Yeah, good. So hello students, I welcome you all to this last lecture of this Abhyas series on fluid mechanics, and today is basically like a cumulative session. We solve the concept, we solve the questions from all the chapters basically, right? Starting from the fluid and its properties to the potential flow, we cover each and every chapter and we touch each and every concept basically in this session. Okay, and many of you during the previous sessions have asked me for some questions on vertex flows, free vertexes, forced vertexes, all these things. So okay, yes, I hope I'm audible, right? So please type in the chat box. Correct? Okay, fine then. So if you see, we basically, since some of you have asked for me some questions on forced vertex flows, okay, and some questions on lift of the cylinder, all these things, so I have kept those questions as well, and in this session we'll definitely solve all the questions from each and every chapter that we have discussed till now. Okay, so are you all ready? Shall we start the session? So please type in the chat box. So shall we start the session clearly? Are you all ready with this? So please type in the chat box, guys. Come on, all of you, whoever is on live, so please type in the chat box and we will start this session soon. Okay, so now fine. So okay, let us start this session directly. So let us start with the first question like this. A plate of dimensions 1.5 meters by 1.5 meters by 0.03 meters, means basically 3 centimeters, is moving with a velocity of 2 meters per second in upward direction, exactly between two fixed plates which are 6 centimeters apart. If the weight of the plate is 500 newtons and the fluid between the plates is water, okay, take kinematic viscosity of water as 5.58 into 10 to the power minus 3 meter square per second. The magnitude of force required to pull the plate upward is dashed newtons basically here. Okay, so let us try to see this. You have two plates which are separated by certain distance. Okay, so let me try to draw the plates. So you have two plates like this. Okay, so you have two plates like this, and these two plates are like this basically. So in between these two plates there is a one more plate which is of some 3 centimeters in width. Okay, so this is a plate which is 3 centimeters in width. Okay, now if you see, this total gap is given to be 6 centimeters. Okay, so from this location to this location, if you see this gap, this is 6 centimeters, correct? So this is 6 centimeters. So this is 6 centimeters. Now this is given to you that this plate is placed in between these two fixed plates like this. These two are fixed and this is also fixed. Okay, so these two plates are fixed and you have placed this plate of width 3 centimeters. Okay, so if you see, this plate is having the width of 3 centimeters. Okay, 0.03 meters, which is nothing but 0.03 meters, which is nothing but 3 centimeters. Okay, so obviously whenever out of this 6 centimeters gap, if 3 centimeters is occupied by the plate, then definitely you have a 1.5 centimeters and 1.5 centimeters thickness on both sides. Okay, so this is going to be 1.5 centimeters, 1.5 centimeters, and this is again going to be, this distance is also going to be 1.5 centimeters basically like this. Okay, so this distance is also 1.5 centimeters. So total it covers the gap of 6 centimeters. Okay, so full fluid mechanics practice. Yes, so this is a complete fluid mechanics practice. Okay, so today's lecture. So now if you see, let us hatch this plate. So this is the plate actually here. Now what you are doing, you are applying some force on this plate to move it in the forward direction. Okay, so you are applying some force F on this plate to move this plate in the forward direction, F. So they are asking you what should be the force that should be applied. So the magnitude of the force required to pull the plate upward is dash newtons. Okay, so this plate is being pulled with some uniform velocity of 2 meters per second. Okay, so it is being pulled at some uniform velocity. So whenever the plate is moving with some uniform velocity, then definitely the net force acting on the plate is 0, because the net acceleration on the plate is 0. So that's why if you see, the plate is subjected to a constant a net force of 0 basically. Okay, so now let us try to identify different forces acting on this plate. And if you see, this complete space is filled with some oil, viscous oil. If you see, there is some viscous oil that is filled all over this location. Okay, so there is some viscous oil which is filled over this location. Okay, clear? So this is some viscous oil. Similarly here also you have certain viscous oil like this. Okay, so there is some viscous oil that is present here in this gap. Okay, so this is your viscous oil. Now, if this is your viscous oil, let us try to identify what are the forces acting on this plate. So, if you take the free body diagram of the plate, for example, like this, then this is the plate. If this is the plate, now this plate will definitely have some weight which will be acting in the vertically downward direction. So, this is W is the weight that is acting downwards. Now, obviously, there is one force with which you are pulling this plate in the upward direction. So, this is F. F is the force which is pulling it in the upward direction. Now, obviously, since on both the sides we have viscous oil, correct? So, मुझे fluid mechanics start से पढ़ने हैं गेट वाला के lecture enough रहेगा अब से शुरू करोगे तो. Yes, even if you start from now, it is definitely sufficient for you. And if you attend, I think crash course is started by Amit Dixit sir. Means in this course we are actually practicing a lot of problems. Okay, I mean the questions, numericals and all. But if you talk about theory, Amit Dixit sir has recently started one crash course kind of thing. So definitely you can attend that. Yeah. Good morning, Chandanji. Hi. So let us focus here. So this is the force with which the plate is being pulled up. Then this is the weight which is acting downwards on the plate. And obviously, since the fluid is in contact on both the sides of this plate, we have two viscous forces that are acting on this plate. So one viscous force is along this edge. Fr, viscous force on the right side, for example, if you say viscous force on the right, and there is also this viscous force on the left face basically. Okay, so there is also some viscous force on the left face, Fl, let us say. Okay, and also if you try to observe one thing, this, yes, buoyancy force is also there definitely, because if you see the body has some dimensions. Okay, 1.5 meters by 1.5 meters by 3 centimeters. So the body has certain volume, so definitely there would be some buoyancy force which is also acting on the plate. Okay, so let us write that buoyancy force also. Okay, so buoyancy force is also there like this. Okay, so this is F buoyancy, for example, if you write F buoyancy. So these are the total forces acting on this plate. Okay, now under the effect of all these forces, the plate is moving at some uniform velocity. Okay, so now if you write sigma Fy is equal to 0, because if you see sigma Fy is equal to 0, and let us suppose you are considering this upward forces to be positive. Okay, now if you see all these viscous forces, okay, so I'm sorry, this viscous forces will actually act downwards, correct? Because the plate is moving in the upward direction, so the viscous forces will actually act in the downward direction. I'm sorry. So we have a viscous force on the right face and also a viscous force on the left face basically. Okay, so this is F right and this is F left. Okay, now it's fine, because you see plate is moving up, so definitely viscous force should oppose the plate motion, so that's why the viscous forces are acting in the bottom direction. So now if you apply sigma Fy is equal to 0, this implies capital F plus capital F buoyancy minus, these are the three downward forces, so minus W minus F viscous on the left side minus F viscous on the right side is equal to 0 here. Okay, so this is basically 0. Now if you see, we need F. So F is nothing but, from this expression, what is the force that you need? W plus Fl plus Fr minus Fb. Okay, so minus the buoyancy force. These are the total forces with which you will get the expression for this F. Now how to evaluate these quantities? Weight. Let us see if they doubt something about the weight. Weight is known. Okay, so did they give you the weight? Yes, of course. If the weight of the plate is 500 newtons, yes, W is given. W is 500 newtons. Let us write the data. Weight of the plate is 500 newtons. Then Fl and Fr, if you see, this is a symmetric configuration, so which means you can understand one thing: whatever is the viscous force acting on the left face, same will be the viscous force acting on the right face also, correct? So and how you actually calculate the viscous forces? Viscous force is equal to shear due to viscosity into area of contact between solid and fluid. Now tell me, if this is a plate, this is 3 centimeters, now this is 1.5 meters and the perpendicular is also 1.5 meters. So in the side view, the area of solid fluid contact is basically nothing but a square of sides 1.5 each, correct? So that's why it's a 1.5 square area. So tau, how will you write this? Mu into du by dy into the flow area. Okay, so this implies the viscous force acting is equal to mu. We have some value for the dynamic viscosity. Then du by dy. If you see, this is a small gap, so in this small gap you can assume the velocity profile is actually linear. Okay, so if you assume a linear velocity profile, for example, at this section, if you take velocity Okay, you take one section here. So at this section, if you take the velocity variation, for example, okay, the velocity variation looks something like this. Let us take a straight line. So this is how the velocity varies linearly in this. Okay, so the velocity of the layer which is in contact with the solid will have the velocity of the solid because of no slip condition. Similarly, here the velocity is 0 because of no slip condition again. So if you see, this velocity profile here is linear actually. Okay, so since this velocity profile is linear, then you can write du by dy is nothing but velocity's difference over this small gap. So that's why you can write this as velocity of the plate divided by 1.5 centimeters, which is 0.015 centimeters, okay, into the area of the plate, which is 1.5 whole square. So now if you see, this is the viscous force on one side. Okay, now since both the surfaces of the plate are in contact with the fluid, this FL and FR both are same. The viscous forces on both the sides is same. So we also got the value of this FL plus FR. If you write as FR, if you write as 2 times of FL, for example, then the viscous force that is calculated is 2 times of that value, which is mu velocity of the plate divided by 0.015 into 1.5 square. Okay, so into 1.5 square. So this is the total viscous effects. Now what is the buoyancy? So what is the fluid here given? So the fluid is some viscous fluid, and the fluid between the plates is water. Okay, so the fluid between the plates is water, means this plate is placed in water. Okay, so if you want buoyancy force, you know, buoyancy force calculation, FB is equal to density of water times G volume of the plate actually here. Okay, so this gives you 10 cube. Did they give you density values? Okay, they didn't talk about the density value, so you can take 10 cube by default. G into the submerged volume, which is 1.5 times 1.5 times 3 centimeters, which is 0.03. So this is the volume. So you got the expression for this, you also got this expression, and you also know this expression. So out of these quantities, this mu and Vp has to be known. So they have talked about this kinematic viscosity. So if you know kinematic viscosity, you can calculate dynamic viscosity. If you multiply this with the density, you will get dynamic viscosity. And they have also talked about this V, 2 meters per second. So that's it, you have all the quantities. So let us go for the simplification. Okay, so this implies F is equal to 500 newtons plus 2 times of FL, which is this value, so 2 times of mu. So how you calculate the dynamic viscosity? Kinematic viscosity is given, fluid is water, so kinematic viscosity into 10 cube, then this 10 power minus 3 gets cancelled, you have dynamic viscosity. So this quantity implies your dynamic viscosity value is equal to 5.58 Newton second per meter square. Okay, so 5.58 Newton second per meter square. So if you substitute 2 times of mu, 5.58 into velocity of the plate is 2 meters per second divided by 0.015 into 1.5 square. So this is the total FL plus FR minus buoyancy force. So density of the fluid into G is 9.81. Let us write the values directly. 9.81 into 1.5 into 1.5 into 0.03. So this is the total expression that gives you the value of this F in newtons. Okay, so let us calculate this value of F in newtons. So this implies your F value is equal to, let us do some cancellations. If you can do, this 10 cube can be eliminated 2 times here and eliminated 1 time here as 15. Okay, and yeah, rest of the things are as it is. Let us go for the calculator. Okay, so let us take the gate calculator and let us, you know, do some calculation. Okay, so let us see what you have here. 3 15s are 45 into 1.5, so 45 into 1.5, so 45 into 1.5 into 9.81 into 9.81. So this is the value 662.175. So this buoyancy force is 662.175. So anyhow, let us save this. Okay, so let us save that value. Then let us calculate this value. 4 into 5.58, 4 into 5.58, 4 into 5.58 into 1.5 square into 1.5 square divided by 0.015. 0.015. So this is the value 3348 plus 500 newtons. This is the weight. So from this total value, you have to subtract previously calculated value. So 3185.825. 3185.825, correct? 3185.825 newtons is the force that you have to apply on the body, so on the plate, so that it moves upward at a velocity of 2 meters per second. Clear? So that's how we got this F is equal to Total force. Yes, buoyancy force also, sir. Yes, we have calculated buoyancy basically. Initially, we have calculated this buoyancy and we have saved the value, correct? If you see, this value is the buoyancy force, correct? 662 point something, 662.175 is the buoyancy force value what we got, okay? I've stored that value and subtracted it from weight plus viscous forces, okay? So that's how I've got this 662, this 3185.825 newtons in this case, clear? So this is a question that involves both viscous effects and also the calculation of buoyancy force, okay? Clear? So please type in the chat box, is this clear to you? A simple question, but again, involvement of both the concepts, Newton's law of viscosity and also buoyancy. Fine. So it's a vertical force. Basically, if you see, it's very simple. Two equations. Then we got the expression. Then we started evaluating expressions for individual terms. That's it. Okay. W, FL. Clear, sir? Next question. Okay. Fine then. So let us see. Let us check the answer. 3185.825. Yeah. 3185. Yes. 3185 is in between both these values. So 31802, 3192. This is the correct answer in this case. Okay. Yes. Fine. So let's go for the next question. Okay. Clear? Nikhil, Suraj, Chandan, all of you guys. But sorry, I couldn't read this. Okay, fine. Yeah. So let us go for the next question. So let us see this question. This is a very good question actually. Okay, so a dam with a curved shape. This is a dam with a curved shape in the figure. The cross-sectional area of the dam is 100 meters square. Means basically, if you take this area, this is the cross-section of the dam actually. So this dam has a cross-section like this. So this area is how much? 100 meters square, and its centroid is at x bar is at 10 meters. Okay, so this x bar, centroid of this dam is x bar, is basically 10 meters. The vertical component of the hydrostatic force Fz is acting at a distance of xp. So basically on this dam, definitely there will be some vertical force, which is nothing but the weight of this fluid which is supported. Okay, so this force is acting at a distance of xp. The value of xp is dash meters, round off to 2 decimal places. Okay, so they are asking you, and this dimension, this length of the dam is given 15 meters. Okay, I think it's blocking, but if you take this point, this length, this base is given 15 meters. Okay, now they are asking you what is the value of this xp. This is actually one previous question in XE, somewhere around 2007-8, something like that. But this is one very good question, so that's why I thought of giving you this here. Okay, now I'll ask you one question. Tell me, for example, if you take some beam, for example, let us say you have taken one beam, some cantilever beam you have taken. Let us see. So you have taken certain cantilever beam like this. Okay, now let us suppose in this cantilever beam, if you have some load, for example, okay, so let us suppose if you have some load like this. If you have certain load like this, it's a UVL, uniformly varying load. Let us suppose you have a UVL, for example. Like this. Okay, now let us suppose you have a cantilever and you have a UVL. Now try to answer this. If you want to replace this complete load with a single point load, for example. Okay, so you know there is load at all over the length of the beam, but if you want to replace this load with a single load, then how actually you do this? Okay, so you actually can replace this with a single load like this here, or somewhere close to this. Yes, so like this you can replace the complete load with a single load. Now F, if you see, now obviously if you want to calculate the about F, you need two things. First thing, of course, F acts vertically downwards, that you know, but if you want to replace F, you should calculate what is the magnitude of F. Okay, and obviously that magnitude of F comes from the area of this figure. Okay, and second, you need to know at what distance you need to place this X, correct? If you should know at what should be the distance at which you have to place it. Okay, so how you decide what is the location you have to place it? Obviously the centroid, correct? You might have done in strength of materials and all. If you have a system of force, for example, like a uniformly distributing, uniformly varying loads, if you want to replace the system with a single point load, then in that case you actually make sure that the effect of this UVL about this axis is same as the effect of this force about the same axis. Means if you see, if this force is trying to generate some moment about this axis, then definitely this force should also be able to produce the same amount of moment about this axis. Okay, so then deciding on that, you will place this distance X. Okay, so now if you take this question of dam, for example, then you know, if I want to see, can I do this? If I want this Fz xp, then can I say, if I calculate some small force df, which is acting at some location df, and of course which is acting at a distance x, for example. Okay, so this is acting at a distance x, this is df. Now if I want this xp value, can I say that this df into x, the total moment which is generated over the complete x, is nothing but f bar or cap this fz which they have given you into xp. Can I adjust? This is some small force z acting in the z direction, so that's why if you see, this is dfz. Now if I take at some small section, if dfz is the force acting on the small area, then the moment of this dfz about this x, so if you sum up all the moments of the df z's that are acting, then can I replace this complete dfz's such that the total moments due to all this dfz's is nothing but the moment due to this fz. Can I do this? The moment due to this, can I use this? So please type in the chat box, can I write this equation? Because if you see about this axis, this dfz is generating a moment of x. So if you integrate this quantity all over the area, then definitely this hydrostatic force fz is multiplied with this xp, correct? I can do this. So now if I can do this, now let us see what is the small elemental force acting on the block. Okay, so the small elemental force acting on the block is how much? You know, hydrostatic force acting on a curved surface is nothing but weight of the fluid supported by that surface, correct? So if you take a small surface, then hydrostatic force acting on that surface is nothing but total weight of the fluid which is acting on that surface. Okay, so now if you take this small elemental area, for example here, if you take out this small elemental area dA, if you take out the small elemental area dA, for you it is just a line, but actually, you know, there is some width of the dam also, so that's why let us take some width of the dam. Then if you take this small area, the force acting on this is dfz. Let us see how we can calculate dfz value. So you have taken some small element, like this, you have taken some small element, and obviously above this there is some height of the water, as per the dam. Okay, so there is some height of the water from the free surface, okay, so this is z, height of the water surface is z from the free surface. And if you see carefully, if you draw a 3D view generally, okay, this is water height. Okay, means basically if you see this, then depending on this, you have on this small area there is some water column, so that's what I have done here. Okay, now if you look at the third view, for example in a isometric view, let us see what happens. So this is the water level that's going to have. Similarly, if you talk about the dam, if you see, okay, I think I have to shorten this a bit. I have to shorten this some more. Okay, and finally, yes. Similarly, let me shorten this also as per the condition. So if you see, this is how we have the water surface. This is how there is some water column on the tank actually here, okay, on this surface, small elemental surface, correct? So please tell me, if you watch an isometric view, then this is how on the surface of the dam, means basically if this is the base of the dam, then on this base, let us suppose if this is the y direction, w is the width of the dam. In the third direction, if w is the width, then this height is z, this is small elemental area dA. So can I say this water force dfz acting on this small area is nothing but on this dam weight of this fluid column which is present above this area? Can I say this? At one particular location, the height of the water column is Z. Means this value, if you see, this value, if you see carefully here, then this is Z. So if this is Z, and of course this element is dx, let us say some small distance you have taken dx on this graph. Of course, for small element, this curvature effect can be neglected generally. So if this is Z, if this is dx and this is w, then can I say that the weight of the fluid which is supported on this small area is nothing but small d of Z acting on this area? So please type in the chat box. Can I say this is the small d of Z that is acting on this area like this at some location? This element is the d of Z, correct? So can I say this? So please type in the chat box. This value is nothing but your d of Z. D f Z actually here. Okay. Now this is what we can write. Okay. Now what is the value of this d of Z? Let us try to see here. D of Z is nothing but weight of the fluid supported by this area. Okay. So what is the weight of the fluid supported by this area? Volume, density of the fluid, water, into G, into this volume of the fluid. So what is the volume of the fluid? Z into dx is the area of this rectangle into width. So Z into dx into W, Z into dx into W. So this is the weight of the fluid which is actually supported on this. Okay. So if you want to take the moment, d of Z into x is equal to rho f g z w into dx into x. So this is the moment. Now if you see, if you apply this expression, now integration over the complete surface area means basically if you take the overall surface area of the dam, then integration over the complete surface area, density of the fluid g z w dx into x is equal to total hydrostatic force. So what will be the total hydrostatic force? Nothing but the total weight of the fluid which is supported by the dam, correct? So if you want to calculate Fz value, total hydrostatic force, you know Fz is equal to total volume. Total volume is nothing but this area which is unshaded out of this. Means if you take this part, now out of this part, the fluid is the area which is not shaded actually. The shaded portion is the dam. So the area which is left unshaded is the fluid. So if I want to calculate the weight of this fluid which is here, then can I do density of the fluid into G into this area which is unshaded into this width W. Can I do that? So please type in the chat box. Can I do that? If I want to calculate the total, the total volume of the fluid which is supported here, then in that case I can say this unshaded area multiplied with the width of the dam actually gives you the total Fz value. Okay, so that's why Fz is equal to density of the fluid into G into this unshaded area. So if you see, this total value is a rectangle, correct? This rectangle height is 40 and this is 15. So 40 into 15 is 600, minus out of this 600, this shaded part, the dam area is 100 meter square. So 100. So this is into W. So this is the total weight of the fluid which is supported by the dam, which means 500 times of W actually here, correct? So this is the hydrostatic force acting in the Z direction. Clear? So this is the hydrostatic force acting in the Z direction, total hydrostatic force acting on the Z direction. So if you see this value, density of the fluid G 500 into W. So this is the total hydrostatic force. This has to be multiplied with XP, this value. Okay. So now let us try to simplify the things. If you take density of the fluid G, these are common terms. You can take out of the integration. Width of the dam is constant. So W is also constant. You can cancel that. Okay. So now what it is left with you is integration of XZ dx is equal to, means over the complete surface A is equal to, width got cancelled anyhow. Okay, so if width gets cancelled, we have 500 into xp, correct? So this is 500 into xp. Now who tells you this value? Xz dx. Okay, so let us see, since width got cancelled, now let us suppose if you take this as a 2D graph, for example. Okay, if you see carefully, this is a two-dimensional graph like this. So this is a two-dimensional graph. Okay, so on which you have some dam profile. Okay, on which you have certain dam profile like this. Okay, so you have some dam profile. Now if you want to see what is this integration xz dx, for example, okay, if this integration xz dx, look, let me draw these areas once again. So here you have some length of the dam and also this. Okay, so now if you see, this is 15 meters. This is 15 meters. Of course, my diagram is not to the scale. So this is 15 meters and this is 40 meters. 40 meters. So now you have taken some small element dx like this of this area 2, for example. Okay, you have taken some small element like this of area 2. Now this dimension is dx and this height is z, of course. So this is x and this is z. Now you want this z into dx. If I say in this two-dimensional area, can I write this z into dx is nothing but this is small elemental area? Correct, I can write this. Okay, so which means in this equation, this is z into dx can be replaced as some small area dA. Okay, now you know this expression is nothing but x into dA. So you know integration x dA is nothing but area into x bar centroid. Correct, from the first moment of inertia, you know integral x dA is nothing but a into x bar, or in other words x bar is equal to integral x dA by integral dA. So that's how we have this relation. Okay, so now if you see this is dA, so this expression is nothing but x into dA. So this gives you, if I call these areas as a1 and a2, then definitely this is nothing but a2 into, let us suppose if the total centroid of this location is present at this value. So let us suppose this is the location of the centroid, for example. So from this, if this is x2 bar, and let us suppose for this function, for this value, for this area a1, let us suppose your centroid is somewhere here. Okay, so let us suppose this is x1 bar, for example. Okay, now definitely you know you actually need, whenever you are doing z dx of this particular area, you need a into x bar. Correct, so if you see, we get a into a2 into x2 bar. So a2 into x2 bar is nothing but 500 into xp. So obviously I'll tell you one thing, this a2 is also 500. Correct, we have just calculated this a2 value, means the shaded, this unshaded portion is also 500, which means you can identify one thing, this xp is nothing but x2 bar, which is nothing but the centroid of that particular unshaded area. Okay, so this is the value which you need. But how to calculate this x2 bar? Let us try to understand carefully. You might have learned about this composite figure. So whenever there are two figures like this, for example, this is combination of two areas, then if there is combination of two areas, you know how to calculate the x coordinate of the centroid. Correct, so how you will do that? X bar is equal to area 1 into centroid of this a1 plus a2 into centroid of this a2 divided with, multiplied with this complete a1 plus a2. Correct, this is what you have learned. Now if you see this a1 plus a2, this is 500, this total is a rectangle actually here. So this is 15 and this is 40. So a1 plus a2 is nothing but the total summation of the areas is nothing but the area of this rectangle. So 40 times 50, which is 600 into x bar. So if you see this is a rectangle, so for a given rectangle, where will be the centroid actually? The centroid is at exactly at the midpoint away from the base. So for this rectangle, the complete centroid lies at 15 by 2 distance. Okay, so that's why this is 15 by 2 is equal to a1 100. You know what is x1 bar? In the question they have given you. Correct, the cross-sectional area of the dam is 100 meters square and its centroid is at x bar is equal to 10 meters. So from this axis, the centroid of this G is 10 meters. Okay, so x bar 1 is actually 10 plus 500 into x2 bar. This is what you actually have. Okay, now let us cancel some zeros, common zeros that exist in every term. Then this is 3 times. So 45 minus 10, 35. 35 is equal to 5 times of x2 bar. This is the centroids. So x2 bar is actually equal to 7 meters. Okay, so this is how we have calculated the centroid of this second part. Okay, so x2 bar is equal to 7 meters. So that's how, since xp and x2 bar both are same, obviously this implies xp is actually equal to 7 meters from the from this z axis. Okay, so this is very good question. You need the concept of hydrostatic forces and also you need the concept of centroids of composite figures. Okay, so that's how this is a very good question, and the correct answer is of course 7 meters, which was given in the examination then. Okay, so this is a very simple question. You see, in single board we have here, we have consumed this space for calculating the centroid, but just one line and clear understanding of the concepts, hydrostatic forces, will actually give you the correct answer. Okay, clear? Rishikesh, sir, I got 132 marks, still not selected in PSU. Which PSU you have written? HPCL? What is the PSU you have written? You can, okay. Yes, area moment about centroid is equal to 0. Yes, of course. If you see, that's what we have actually calculated. Okay, this is the first moment. Centroids are nothing but the first moments. Okay, sir, abhi kitni class hogi? This is the last class of this course. Okay, this is the last class. Okay, previously you have some 9 lectures on individual topics. This is like a cumulative session. Okay, clear? So please type in the chat box. Did you all understand how we got this XP is equal to 7 meters? Okay, so please type in the chat box. Is this clear to all of you? Did you all understand how we got this, 7 meters in this case? Yeah. Okay, fine. So this is how, it's a very good question actually. It was a previous question in XC, but I thought of discussing this because it involves multiple concepts actually like this. Okay, so basic thing is, if you want to replace a force system, you have to balance the moments. So that's why this integration over the complete area of the dam is equal to this value. And we have done some calculations, and finally we have calculated the centroid of the composite figures. Okay, now let us see this third question. Water flows downward in a pipe of 600 mm diameter at a rate of 2 meter cube per second. It then enters a conical duct as shown in the figure. So here is the figure. So basically, I think it is a bit light, but I hope you can understand this. Okay, so Q in this location is equal to 2 meter cube per second. Okay, Q is equal to 2 meter cube per second. Okay, so Q is equal to 2 meter cube per second. Now this is a 600 mm diameter, and this is a conical frustum kind of thing, and here it is 300 mm. Okay, now this is 300 mm, and this height of the cone is basically 1.5 meters. Okay, so now let us try to understand this. Now then it enters a conical duct as shown in the figure with porous walls such that there is a radial outflow with flow velocity varying linearly from 0 at A to 1.5 meters per second at B. So what's happening basically here, by the time the flow is coming in this direction, because there is a flow in this direction, so what's happening is, in this direction at this location the flow velocity is 0. But by the time the fluid came here, the radial flow is 1.5. Look, means basically out of this cone, means if you take a conical duct like this, then fluid is coming radially outward from all over the circumference of the cone. Okay, so let us try to understand this. So the velocity is linearly increasing from 0 to 1.5. Now what they are telling you, the rate of flow at B coming out from the conical duct is dash. The rate of flow at B coming out from the conical duct actually here. Okay, so what is the flow that is coming out at this section B from the conical duct? So if you want to know this value, you have to calculate what is the outflow from the cone. Okay, so you have to calculate what is the outflow value from the cone actually, from the discharge. Okay, so now if you want to calculate the outflow from the cone, yes, it's simple. So you generally velocity is not same, so obviously the discharge at different heights will be different. So let us suppose if you take a section, for example here, let us take a section like this. Okay, and let us suppose this is the reference, the starting point of the cone is the reference. Now let us take some y direction. Okay, so this is the y direction. Okay, now if this is the y direction, now what's happening here, initially at this location y is equal to 0, you can understand, at y is equal to 0 the radial velocity is 0 obviously. Okay, this is also 0, because if you see at this location there is no radial velocity, but at a distance of y is equal to 1.5, this length of the frustum is also 1.5. so at y is equal to 1.5 meters, this v radial is also 1.5 meters per second. Okay, so this is also 1.5 meters per second. Okay, now they are asking you what is the discharge that comes out of this section B when this diameter is actually 300 mm. Okay, so this is what they are asking you. Now let us see, if you want to calculate the discharge, let us take some small element of height dy, for example here. Okay, so let us take this small element of height dy. So let us suppose this dimension is actually dy in this case. Okay, now if you want to calculate the small discharge, because discharge at B is nothing but discharge at A minus this outflow from the frustum. Okay, so if you want QB is nothing but QA minus some discharge which is leaving. So if QA is already given 2 meter cube per second, so if you can identify this Q, that's it, your question is done. So let us see how to calculate. So from this small element there is definitely certain radial flow that is coming out. So if you see what is the flow rate? So dq is equal to how much? Dq is nothing but, the flow is radial, so area perpendicular to the radius is nothing but the circumferential area. So if you calculate dq is nothing but flow velocity Vr at that location into the area available. So let us suppose the diameter of the cone is changing. So let us say at this location the diameter is d, for example. Okay, this diameter is d. So the circumference at that location is pi d into dy is the height of the cone, actually height of that small part. So this is actually the relation for getting the small discharge. So obviously you have to integrate this expression from 0 to 1.5. That's it. Okay, so this implies total discharge q is equal to integral y is equal to 0 to y is equal to 1.5 meters per second Vr into pi d dy. That's it. Now the only thing is Vr is not a constant, it is changing along with y direction. Similarly, this diameter d is also not a constant, it's also changing along the y direction. So your job is to get this d and of course v radius in terms of y. Okay, so if you can write this diameter and radial velocity in terms of y, that's it, your question is finished. Then it's just a mathematical question. Okay, so now let us try to identify how we can write that. So first, diameter is d1, diameter is d2, this is the y direction. So many times in the first lecture in fluid and its properties and all, I have told you, whenever there is a first term like thing like this, for example, then if this is the x direction, I told you, if this is d1 and if this is d2, and let us suppose if the total length is l, for example, then I have told you at any location x away from this starting point, diameter d is given by d is equal to d1 minus d2 by L into x. I have shown you this based on this slope of the line in the first lecture, correct? So area how pi dy, because if you see the first term of the cone is like this. Okay, so whenever the first term of the cone is like this, whenever the fluid is coming out, then whenever the first term is like this, this area of the circumference is the area available for the radius. Okay, so that's why whenever fluid is coming like this, this circumferential area all over the 360 degrees the fluid is coming. So pi d is the circumference for some small height pi dy. Okay, clear? So that's how we got pi d into dy actually here. Okay, so d is equal to d1 minus d2 by L times of x actually here. Okay, so now if you see, we have taken this as constant in every, almost in all our things. So d is equal to d1 minus kx is what we have taken. Okay, so d can be written as d1 minus kx. Okay, now what about this guy Vr? It's given the velocity such that there is a radial outflow with flow velocity varying linearly from A. So the velocity is varying linearly actually. Okay, so if velocity is varying linearly, let us say Vr is equal to A plus By, for example, because velocity is varying linearly. Here starting from 0 to here at 15, this is a linear variation. So let us see, there are two constants. To get these two constants, you have two boundary conditions. Let us substitute. So first boundary condition gives you 0 is equal to A plus B into 0. Obviously this implies you A is equal to 0. Next, second boundary condition, 1.5 is equal to A is 0 anyhow, so B into Y value is also 1.5. So this gives you B is 1 actually. Okay, so B is 1. So this means from these two boundary conditions, if you calculate this A and B constants, we get V radial is nothing but a function which is Y directly. Okay, so V radius is nothing but it depends on just Y like that. Okay, so let us substitute Vr and also this capital D in terms of Y. So if you substitute, let us see what comes out. This implies Q is equal to integral 0 to 1.5 Vr, which is nothing but a y, times pi into d1 minus k times of y into dy. This is what you have. Okay, now if you integrate this, pi is a constant, integration of d1 into y, d1 into y square by 2 minus this k is a constant here, so k into y is y square, so integration of y square is y cube by 3 within the limits 0 to 1.5. So this is the total discharge that comes out of the plate at that comes out of the conical section actually here. Okay, so if you simplify this, pi times of d1 into 1.5 square by 2 minus k by 3 times of 1.5 whole cube. Okay, we have this 1.5 whole cube minus 0. When you put y is equal to 0, this is total 0. So let us calculate the discharge. Q is equal to pi is constant. No, sorry. Yes, pi is constant. Then 1.5 whole square can be taken out. 1.5 whole square can be taken out. Then you have d1 by 2 minus k into 1.5 by 3. So that can be written as k into 0.5. Okay, so because if you see 3 cancel this 1.5, 0.5 times, that's it. Okay, so what is the value of k? K value, which is nothing but k by 2 actually. So this k into 0.5 by is nothing but k by 2. We can write that as k by 2 minus k by 2. So what is d1 minus yes, so we have written k by 2. Okay, so what is k value? D1 minus D2 by L. So what is D1 minus D2 by L? Let us write k value here. Q is equal to pi times of 1.5 whole square into D1 by 2. So what is D1? 600 mm. So if you convert that to meters, 0.6 by 2 minus k. So what is k here? K is D1 minus D2 by L. So D1 minus D2, 300 mm. So half of that is 0.3. 0.3 divided by 1.5. So 0.3 divided by 1.5 multiplied with the 2. So this value is 3 and this is 0.3. So if you simplify, this is 0.3 and this 3 times of 0.3 is 0.1 totally. Okay, so if you simplify, Q is equal to pi times of 1.5 whole square into 0.3 minus 0.1, which is 0.2. These many meter cube per second. Okay, so this is how we calculate the flow rate which is actually leaving the cone. It's very simple question actually. The only thing is you need to do the integration little carefully. Okay, and converting this VR and D in terms of Y. So if you do that, this is the discharge to the cone. So what is the discharge to the cone? 1.5 whole square, 1.5 square into 0.2 into 0.2. 1.5 whole square is also there. It got split up, I think, into pi, correct? So into pi is also there. Okay, so into pi. So 1.4137. 1.4137 is the value of this Q. So Q is equal to 1.4137. 4137 is what you actually have in, of course, in meter cube per second. This is in meter cube per second. So Q we have identified, QA is known, so QB can be calculated directly. Okay, so this has to be subtracted from total 2 meter cube. So 0.5862 meter cube per second is the flow that actually comes out. Okay, so from the duct. Okay, they are asking you from the duct directly. Okay, from the conical duct only they are asking you directly. So this means basically they are asking you this Q value. Okay, so Q is how much? Because they are asking you from the conical duct what is the discharge. Okay, so that's why if you see what is this value? 1.4137. 1.4137 meter cube per second. Okay, because they are asking you what comes out as the discharge as the conical duct. Okay, yes, fine, it's a simple question, but of course, yeah, you need to apply little mathematical knowledge for integration. That's it. Okay, but this is a nice question because what happens obviously is as the flow velocity increases in the chamber, obviously the radial velocity also increases in general case. Okay, so that's why we have taken some most general case, because what happens whenever this is a vertical section, obviously when the cone is means whenever the duct is conical in shape, because of the decrease in the area of cross section, the velocity of the flow increases. So whenever the velocity of the flow increases, whenever there is a pore, obviously the outlet velocity also increases. Okay, clear? So that's how we have calculated this. So they are asking you Q value directly. They are asking you Q value. Okay, so 1.41 something, whatever we got, 1.41 plus. Okay, so this is actually a good question, but a simple question. Okay, so clear? Shall we go for the next question? So as Nikhil, Ashish, so please type in the chat box. Can we go for the next question? Clear? So let's go for the next question. Okay, this is the next question. Yeah, let us try to see here. Okay, so now see, at a radial location R1 in a horizontal plane, the velocity of a free vertex becomes same as that of a forced vertex if the pressure difference between R1 and R2 being another radial location in the same horizontal plane with R2 more than R1. Okay, so in the forced vertex becomes twice that in the free vertex, determine R2 in terms of R1. Okay, so this is what they are asking you. Means basically you have a horizontal plane, so there is a horizontal vertex flow. Means in a horizontal plane means there is no difference in Z. So in a horizontal plane, what's happening at two different locations, R1 and R2, we have some things. Okay, so let us see. At a location R1, the velocity of a free vertex becomes same as that of a forced vertex. So let us suppose if you talk about free vertex and forced vertex, free vertex and forced vertex. Now let us see what comes out. At any radial location, the value of velocity is nothing but c by r1, correct? So this is the radial this is the velocity, and at this forced vertex we have r1 times omega. This is the forced vertex case. Okay, so v theta is equal to r1 into omega. Now given that these two things are equal, which means this implies c1 by c by small r1, c by small r1 is equal to r1 times of omega. So which means c by omega is nothing but r1 square. So this is the relation. Okay, they have given you this. Now they have given you one more condition. What is that? The pressure difference between R1 and R2 in the forced vertex becomes twice that in the free vertex. So delta P between two locations in forced vertex is equal to 2 times of that in the free vertex. This is what they are talking you, correct? Now let us see what is the pressure difference in case of this forced vertex. Rho omega square by 2 times of, if the pressure difference is P2 minus P1, then R2 square minus R1 square. Okay, so this is the pressure difference between two radial locations in the vertex flow, because the potential heads are zeros. Actually, if potential heads are there, of course you might have got plus Z2 minus Z1, but since there are no potential heads, so there is nothing, it's a horizontal plane. Okay, so this is equal to 2 times of P2 minus P1. So in a free vertex case, if you have P2 minus P1, then how you write this P2 minus P1? Rho C square by 2 times of 1 by R1 square minus 1 by R2 square. So this is how you actually write the pressure difference in case of a free vertex flow. Okay, so basically it should have the dimensions of velocity square. Yes, so rho C square by 2 into 1 by R1 square minus 1 by R2 square. This is the pressure difference. Means basically if you see, delta P is nothing but P at location 2 minus P at location 1. Okay, means basically P at R2 minus P at radial location 1. So this is how we write the difference in forced vertex and also in the free vertex. Okay, now let us see, these two are, this equation is there. They are asking you what is the relation between radial location 2 and radial location 1. So let us cancel few terms. This rho gets cancelled. Let me cancel with different ink so we can see the difference clearly. Densities gets cancelled, 2 gets cancelled. So what you have is omega square times of R2 square minus small r1 square. So this is equal to 2c square times, if you take LCM, R2 square minus r1 square divided by small r1 square into small r2 square. Okay, so this is what you have. Now let us simplify this. R2 square minus r1 square and this term can be cancelled. So this implies what you have here, c square, okay, 1 is equal to c square by 2 times of c square by omega square. So c square by omega square is nothing but r1 to the power 4. 1 by r1 square into r2 square is what you have. Okay, so if you make some simplification here, this turns out to be r1 square. So from this equation what you have is, if you bring this, if you keep this 2 here and if you shift r2 and r1, we have r2 square by small r1 whole square is equal to 2. So this implies r2 by r1 is equal to square root of 2 actually here. So this gives you finally the radial location at 2 is root 2 times of radial location at 1 actually here. Okay, so this is how we can calculate this. So r2 is equal to root 2 times of r1. Okay, Rajnit, Rishikesh, which branch are you? Okay, I think some personal discussions, you carry on. So this is how we have, so square R2 is equal to root 2 times R1 is the correct answer here. Okay, so you might have seen this delta P difference, pressure differences in free vortex and forced vortex for different things. Basically, when people talk about vortex flows in comprehensive courses in all these locations, you might have definitely gone through this. So this is how we calculate the delta P forced, and this is delta P free, and some mathematical simplification easily gives you that this radial locations should be at a distance of R2. Means the relation between the radial locations for this kind of situation is R2 should be square root of 2 times of R1. That's it. Okay, so whenever this happens, obviously the forced locations, means the pressure in the forced locations should be the pressure difference in the forced vortex is twice that of the pressure difference in the free vortex. Clear? So let's go for the next question. Let us see. A closed cylinder 0.4 meters in diameter and 0.4 meters in height is filled with oil of specific gravity 0.8. Okay, if the cylinder is rotated about its vertical axis at a speed of 200 rpm, the thrust of oil on the bottom cover of the cylinder is dash newtons. Okay, so basically there is some container which is closed and it is completely filled with oil of specific gravity 0.8. okay, now what happened, this container is rotated about its vertical axis at a speed of 200 rpm. okay, so there is a rotation of this container. So whenever this container is being rotated, then the thrust of the oil, what is the force that the oil exert on the bottom surface of the container? So this is what we actually need. Okay, so if you need this, look, let us suppose you have a container, you have some container like this. Okay, you have a container in which you have some oil filled, you have some oil filled here. You have some oil filled. Now what's happening, this container is revolved about this axis, about its axis at 200 rpm. So there is some angular velocity with which you are revolving this container, so omega. So what is n? 200 rpm, right? 200 rpm is what they have given you. Yes, 200 rpm. So if this is 200 rpm, then in that case your omega value, angular velocity, is nothing but 2 pi n by 60 or pi n by 30, you can say pi n by 30. So this gives you 20 times pi by 3 radians per second. Okay, so you have this radians per second unit. So this is the angular velocity at which this is rotated. Now whenever this is rotated, if you take a pressure at a distance of, means basically it's a forced vortex, so if you take pressure difference between these 2 points, means on the just first layer immediately, then what happens here, here the pressure is 0, because if you see the radial location is 0. So pressure at any location at any radius smaller, means if you take this radius for example, then if this radius is at a distance of, if this radius is at a distance of smaller, then in that case what happens is P at that location is, how much is this? P at that location is rho times omega square r square by 2. Okay, so P at this top location is basically, means at this point the pressure P is given by rho times of omega square r square by 2. Just now we have seen. Okay, now if you take the same bottom point on the same vertical line, means basically at the same radial location, if you take a bottom point here B, let us say, then at this location the pressure is due to this pressure which is because of this rotation, plus there is a fluid of datum H. Okay, so that's why if this is the height of the cylinder, if this is the height of the cylinder, then in that case pressure at this location B is nothing but, pressure at this location B is nothing but pressure due to this rotation, plus because of this fluid column height there is certain pressure which is acting on the base. So rho fluid G H is what you actually have. Okay, now this pressure acts at this particular point. So if you take a top view of this, for example, if you take a top view of this, if you take a top view of this, this is the cylinder. Okay, so if this is the cylinder, then at a radial location r smaller, at a radial location smaller, let us see, at this radial location smaller, okay, so at this radial location smaller, let us suppose if you take some small element. Okay, so let us suppose if you have taken some small element like this, for example, then in that case this thickness, if I take this as small dr, the small difference in the radius dr, and from this center this radius is r. Okay, now obviously this shaded area, this shaded part, the small area of the elemental ring actually lies here. So if you see, this area is the small area dA, which is 2 pi small r times dr. Okay, so now if you see at a radial location r, this much pressure is acting on this small elemental area. So if you want to calculate the total thrust, how you can calculate? You can integrate this effect. Okay, so the small elemental force F acts on the plate over this small area is nothing but F or PB into the pressure is acting all around the area, which is 2 pi r times of dr actually. Okay, so now if you want to integrate this, the total force, the total thrust is how much? The total thrust is how much actually here? So the total thrust is equal to F, which is of course equal to integration of this df. Okay, so this implies F is equal to integral PB. What is the expression for PB? Rho omega square r square by 2 plus rho gh times of 2 pi smaller dr, and of course you can see the radius can change from 0 to infinity, so that's why the integration limits are from 0 to capital R. Sorry, radius can change from 0 to capital R. So this is the expression how you calculate the total net vertical force acting on the base of the cylinder actually. Okay, so now if you do this integration, F is equal to rho omega square by 2 into 2 pi is constant. So rho omega square by 2 into 2 pi is a constant basically here. So r square into smaller, so r cube, integration of r cube is r to the power 4 by 4. That's it. Okay, so after substituting the limits of course, so for the first term rho omega square by 2 is constant, this 2 pi is also constant, small r square into small r gives you r cube, integration of this small r cube is r power 4 by 4, with this limits you get this, plus for the second term rho gh, height of the cylinder is also constant, 2 pi is also constant, so rho gh into 2 pi, this is a constant, integration of small r is r square by 2, so if you substitute the limits we have capital R square by 2. Okay, so obviously if you do some simplifications, I think you can get some results. So 2 gets cancelled, and 4 is left over here, so similarly 2 gets cancelled here. Okay, so now if you take some common terms, rho is constant in both the common in both the terms, pi is also constant, so rho pi is also constant, then r square, you can take one r square also constant. Okay, so density into base area, which is pi r square, and if you write the remaining terms, rho pi r square we have taken, so omega square r square by 4 is what you have, plus, correct, because you see rho pi omega square r power 4 by 4 plus, from here rho pi r square if you take out you have gh. That's it. Okay, so we have gh, right? We have only gh term here, g and h are the terms which are left over here. So let us do the simplification. You have the values, let us do the simplification here. So this implies F is equal to density of the fluid. So let us take the details. Density of the fluid. So basically what is the fluid? Specific gravity 0.8. So let us suppose the density of the fluid is 800 kg per meter cube. 800 kg per meter cube. Then what we have, still what else we need? Pi is constant, radius, r value, how much? 0.4 meters in diameter, means this capital R value is 0.2 meters. Okay, and then what else we need? We need omega value. Omega we have calculated 20 pi by 3, so omega is 20 pi by 3 radians per second. So this is what you have, radians per second. Then capital R we got, G is constant of course. G, how much did they ask you to take? Nothing they have mentioned, so 9.81 by default. Then H, capital H. What is the height of the cylinder? 0.4 meters. So H is also 0.4 meters. So you have all the values. Now let us just substitute and let us get the answer. Okay, so density 800 into pi into small r square, so 0.2 square, multiplied with omega square. Omega square is 400 pi square by 9. Omega square, small r square. So small r square is again 0.2 whole square divided into this 4 is also there over here. Okay, so omega square r square by 4 plus 9.81 into h, which is 0.4. That's it. You have to just calculate this value and the answer is going to be in newtons. What are the units they are asking you? They are also asking you the answer in newtons. Okay, so let us simplify this expression. Let us try to do some manual simplification before we go straight away. So this is 100. So this is 0.04. Okay, so this is 0.04. So this total value gives you 4. So 4 pi square by 9. Similarly here, this this 100 will cancel this 4 times. Okay, so total you have 32 here. Okay, so 32 into pi into this complete expression. So first let us calculate this. 4 pi square by 9. 4 pi square by 9. 4 into pi square. So 4 into pi square by 9. Okay, so 4 into pi square by 9 plus 9.81 into 0.4 plus 9.81 into 0.4. So if you do this, we got 8.3104. So multiply it with 32 into pi. So 32 into pi. So multiply this with 32 into pi. Okay, so if you do this, we got 835.46 newtons. 835.461. I think we have 835.46 newtons. So this is basically the force acting on the container. Okay, so if container is open, then what happened? Please explain, sir. Yes, definitely if container is open, even in that case you have the same analysis, but of course along with that you also have the atmospheric pressure. So plus P ATM will actually add at this location. Okay, got it? Since the container is closed, it's completely filled with fluid, the free surface is at 0 pressure is what we are assuming. But let us suppose if the container is open, then in that case we have P ATM also here. Okay, fine. Okay, so this is what we have here. So the total force acting on the container on the bottom is actually equal to FB. You can say FB DFB on the bottom face, for example. So this total force acting on the bottom of the container FB is given by this value. On the top, if they ask you, then in this complete calculation what happens? If they ask you on the top, then definitely this H value is 0. You have only this particular term. Okay, in that case, if it is free vertex, then you write P is equal to rho c square by r1 square. Okay, so we will write, if it's a free vertex, P is equal to rho c square by r1 square. Okay, rho by 2 you have actually, so rho by 2 c square by r1 squares. If they give you the radius at particular location, means if they give you velocity at some particular location r1, you have this c value. Okay, instead of this c square by r1 square, you can replace with that velocity square value. Okay, but generally cylinders, they don't rotate on their own. Okay, generally it's forced vertex case, so that's why we have talked about this. Clear? Anyhow, I'm going to erase this if it's a free vertex, but anyhow here this is the case of a forced vertex. That's it. Okay, so sometimes if you want, you can remember this formula, but generally it's just 1-2 steps integration. So if you see, writing this in exam takes hardly half minute, then this is one more 20 seconds and you can go for integration. Okay, so also if you want, you can remember this also. Okay, if they ask you on the top surface, then this term, second term, won't be there because there is no pressure head on that time, so H will be 0, so there is no term on the last. Okay, so you have just rho into the area of the circle into the tangential velocity square by 4, means v square by 4 at this location. Okay, so that's how we get this value. Clear? Okay, now did you understand how to calculate the forces acting on the faces of the container? Okay, similarly, if you talk about the force acting on this side wall, basically if you see there is a side wall for the container, so if you want to calculate the force acting on the side wall, then this pressure at this particular location is actually given by, means at a depth d, at a depth h, for example, if you see the pressure acting at this location is nothing but capital R, because the point has already reached here, so rho omega square capital R square by 2 plus rho g y, for example, into this pi d into dy. So again integrate y equal to 0 to h, you will get the total thrust acting on the side wall of the container. Okay, so that's how you'll get it. So next, let's go for the next question. So let us see this question. Water flows through a circular nozzle, exits into the air as a jet. Water flows through a circular nozzle basically here. So there is some circular nozzle, exits into the air as a jet. Okay, exits into the air as a jet and strikes a plate as shown in the figure. The force required to hold the plate steady is 70 newtons. So basically this force what you are fixing this is actually 70 newtons. Okay, so if this is 70 newtons, then assuming steady frictionless one dimensional flow, then which one or more of the following statements is R2. Okay, this is an MSQ. Fine, this is an MSQ. So you can have different possible things. Okay, so there is a manometer, there is a pipe flow, and there is a fluid linear momentum equation that got involved in it. So let us try to solve this question. Okay, so now if you try to solve this, first of all, let us start an analysis from this location. If you take some control volume like this is a control volume, for example. So if you take your control volume like this, because this is the location in which the fluid is changing its momentum, then we have seen many cases that the total force exerted by the jet, which actually slides smoothly, is nothing but rho a v square. Okay, sorry sir, will you give recorded video solutions for FMXC test series? Yes, definitely. Okay, no issues, we will give recorded solutions. So see here, this control volume. So if you see, basically in this control volume, our fluid jet is actually sliding smoothly over the plate. Okay, so whenever it is sliding smoothly over the plate, we have seen if this velocity is v, for example, and if the fluid is moving out in the same velocity v, because it is given frictionless, so then we have seen the total force exerted on the plate is nothing but rho a v square. Correct? So if you see from this location, let us suppose if this is d1, this is d2, and let us suppose if flow is coming with velocity v2 like this, then the force which is needed, the force which is exerted on the plate, F on plate, is nothing but rho a v2 square. Okay, so this is rho a into v2 square, and of course that's the force what you are applying, F. Okay, so now let us calculate what is the velocity v2. It's given, F value is given to you. How much is this? 70 newtons actually. Okay, so 70 is equal to rho, the fluid is water, so density is 10 cube. They haven't talked about density, so density is 10 cube. Area of the jet, so if you see, this is coming out from a 3 centimeter diameter pipe. Okay, so let us suppose if the jet is of same diameter 3 centimeter, because if you see the exit is to it 3 centimeter, so the jet comes out as a 3 centimeter diameter jet. Okay, so that's why if you see pi by 4 d square, 3 centimeter is nothing but 0.03 meters, so whole square. So this is the diameter into v2 square actually here. Okay, so that's why if you simplify this, what can we get? 70 into 4, 280 is equal to 10 cube into pi into, this can be written as 9 into 10 to the power minus 4 times v2 square. Okay, so if you simplify this, let us see what comes out. This 10 cube gives one more 10 here, so divided by 10, you can say you will have a divided by 10. So this implies v2 square is equal to 2800 divided by 9 times of pi actually here. So if you simplify this, your v2 value you will get in meters per second. So let us simplify and let us try to get this value. 2800 divided by 9 times of pi. Okay, so this is what you have. So 99.029. So 99.029, and you need to take a square root of this. Okay, so take a square root of this, 9.9513, 9.9513 meters per second. Okay, so this is the velocity with which the jet is actually impinging the plate. Okay, so v2 is equal to 9.9513. okay, so if you see, let us check the options. Velocity of flow in 10 centimeters pipe. 10 centimeters we don't know yet. We need to see. Velocity of flow in 3 centimeters pipe is 9.96. Yes, we got the same value, 9.951. Okay, they were close, 9.96. So we can see this is the correct answer. This is the correct answer. B is correct. Next, C, manometer deflection we have to calculate. Velocity of flow in 3 centimeters pipe is 4.5. This statement is wrong actually. Okay, and they are asking you for the correct statements now. R2. Okay, fine. They are asking you for the correct statements. So now this is 9.95 meters per second. Okay, this is correct. Now out of these two, let us check velocity of flow in the 10 centimeters pipe. So let us check what happens in the 10 centimeters pipe. If you apply continuity equation, because if you see, whatever the flow that causes this section, same should be the flow that causes this section. Means if you take something like here and also here, if you take two sections here, 1 1 and 2 2, and if I name this points, if this section as section 1 1 and section 2 2, then definitely the flow volume through these two has to be same, because this is in series. So now if you see this from continuity equation, from continuity firm continuity, the fluid is water, so incompressible, let us suppose. Then A1 V1 is equal to A2 V2, which gives, if we cancel pi by 4, we have D1 square V1 is equal to D2 square V2. So what about V1? V1 is nothing but V2 times of D2 by D1 whole square. Okay, so let us check the value. So V1 is equal to V2, some value got 9.9513 times of D2 by D1. This is 3 centimeters, this is 10 centimeters. So this square, you will get the answer of V1 in meters per second. Okay, you will get the answer in meters per second. So let us see this. So 3 by 10 is 0.3. So this value multiplied with 0.3 square. Okay, so 0.8956. 0.8956 is the velocity at this location. 0.896, you can say 0.896 meters per second. So let us see what is the statement. Velocity of the flow in 10 centimeters pipe is 0.9. Okay, so yeah, if you round off, it is 0.9 meters per second. So this statement is also correct statement. Okay, because if you see, if you round off to 1 decimal, this is 0.9 meters per second. Okay, so that's also true. Now what they're asking you next, manometer deflection. So if you want to calculate manometer deflection, you should know what is the pressure difference here, correct? And given this is mercury, and of course nothing data is given, so we'll take mercury is 13.6 by default, specific gravity. Okay, so let us see. If you apply Bernoulli's equations at these 2 points in the flow, so let us see, and let us see what happens here. So this total height of the fluid gets cancelled on both sides, because the pressure head due to this height of the fluid and this height of the fluid is same. So that's why if you see, the pressure difference between these 2 points is same as pressure difference between these 2 points. Okay, so pressure difference between these 2 points. So let us take the datum here. So if you take the datum here, xx for example, then the pressure here is P1 and the pressure here is P2 for example. Okay, so because if you see, this common fluid, this fluid is common on both the limbs, so it gets cancelled out. So if you apply Bernoulli's equation, applying Bernoulli's equation, so if you apply Bernoulli's equation basically here, let us see what comes out. So P1 by OZ plus V1 square by 2G plus Z1 is equal to P2 by rho Z plus V2 square by 2Z plus Z2. Now the pipe is horizontal, so assuming frictionless and all, this datum heads gets cancelled. So P1 minus P2, this is density of water actually. Okay, because water is the substance which is flowing in that. Okay, so P1 minus P2 by density of water into G is equal to V2 square minus V1 square divided by 2G. So Gg gets cancelled of course. So now if you see the pressure difference from this manometer, let us see the equations from the manometer. So this is the manometer. So P1, so since this is a hydrostatic case, the pressure at this location A and the pressure at this location B should be same. Okay, so PA is nothing but P1 plus rho water GH, PB is nothing but P2 plus rho mercury GH. Okay, so let us see. P1 is equal to, or PA is equal to, or P1 plus rho water GH, this should be same as P2 plus rho mercury GH. Okay, now if you take the difference, P1 minus P2 is nothing but P1 minus P2 is actually equal to GH times of density of mercury minus density of water. Okay, so if you substitute here in terms of P1 minus P2, you can get this P1 minus P2. If you substitute there, let us calculate. Let us take a new slide. Okay, so see here. So P1 minus P2 is actually how much? Sorry, rho mercury minus density of water times GH divided by density of water times G. This is equal to V2 square minus V1 square by 2 is what you have. Okay, I think this G is not there here, so only we have by density of water here. Okay, so divided by 2 actually here. So now if you see, you know, we need to calculate this H value. So how we can calculate this H value? This term you can write this 1 and this as 13.6, because this is specific gravity and H, everything is known to you. So only thing you need to know is H, V2 square minus V1 square by 2 times of 12.6 into G, which is 9.81. So this is what you actually have. Okay, G comes here, and also this difference multiplied with the 2. So 2 into 12.6 into 9.81. So if you calculate this, you will get the value of H in meters. Okay, so you'll get the value of H in meters. Let us calculate what is the value directly. V2 square. This is V1, correct? So V1 square, this has to be subtracted from V2 square. So what is V2 square? So let us do the calculation, no issue. So V2 square, 9.9513 square minus V1 square. So what is V1 square? 0.896 square. Okay, so 0.896 square. Okay, so you got this value. So this is V2 square minus V1 square actually. So divided by 2 times of 12.6 into 9.81. Okay, so if you make this calculation, you got 0.397 meters. So 0.397 meters. So that means the manometer has shown a deflection of 39.7 centimeters actually. Okay, so 39.7 centimeters is the deflection shown, or 39.7 or 0.4. If you 39.7, if you round off 40 centimeters, so that is 0.4 meters. So statements A, B, C are actually the correct statements in this case. Okay, so see, to solve this question, we have used linear momentum equation, we have used mass conservation, we used Bernoulli's equation, and also we used the concept of manometer. Understood? So that's why this is basically it's a good question actually. So we have a lot of things that we actually came up with. So we have used all these cases for the manometer and all. Okay, so H is equal to 0.397 meters. Okay, so that's how we can solve this question basically in this case. Clear? I hope it's understandable to you. Simple question, but again you need some understanding. Okay, clear? So please type in the chat box, is this understandable to you? All of you, Teja, Nikhil, Surat, all of you. Okay, fine. So let's go for the next question. So let us go for the next question. Water at 60 degrees Celsius flows between two large flat plates. The lower plates move to the left at a speed of 0.3 meters per second. So the upper plate is fixed. The plate spacing is 3 mm and the flow is laminar, of course. The pressure gradient required to produce a zero net flow at a cross section is dash. So at any given cross section, you have to look at a zero net flow. So I have told you basically when we are talking about laminar flows, means basically internal viscous flows, I have given you this expression. So let us suppose if you have two plates. If you have two plates, for example, like this, okay, so if you have two plates like this, then if you have these two plates, now let us suppose if this plate is fixed and this plate is moving towards left, correct? They have given you this is moving towards left like this with a velocity u infinity, let us say. Okay, so this is u infinity. So we defined one particular coordinate axis for some equations. If you take x, positive x is in this direction and positive y is in this direction, then we came up with one velocity profile. If this is x and if this is y, then at any location at elevation y from the surface, at any location y from the surface, the velocity of the layer is given by u, which is related with u by u infinity is equal to y by h plus alpha times of y by h into 1 minus y by h, correct? So this is the velocity profile that we have written here, and if you see, this height is actually h. What we are talking is actually h, this height basically here. Okay, so this height is actually h. Okay, so this height is h. So whenever this height is h, we have understood this velocity profile. And what about this h value? And of course there is some viscous fluid which is filled all over. Okay, so there is some viscous fluid which is filled all over here. Clear? All over between the plates there is some viscous oil of some viscosity. Okay, so there is some oil with some viscosity like this. Okay, so we have some viscous oil. Now if you see okay, we'll see basically. Okay, so now if you see, this is the expression, and you know, for net flow and discharge at any section I have given you. So discharge at any section is equal to u infinity times of h into 1 by 2 plus alpha by 6. This is the total discharge, and alpha value is nothing but h square by 2 mu u infinity into the pressure gradient value in this x direction, okay, basically in the flow direction. So these are the common expressions that we have actually I have given you that day. So if you see, this is the velocity profile and this is the value of alpha and this is the discharge at any given section. Now they are asking you what should be the pressure gradient value so that at any given section the net flow is actually 0 here, okay. So if you take this particular section, if you take a particular section actually somewhere like this, so at this section, if your net flow has to be 0, then definitely alpha value has to be -3 for q is equal to 0 at this section, correct? Because what happens whenever alpha is negative, you have certain velocity profile like this. Your velocity profile will be something like this. Okay, this side the plate is moving in a different direction. So basically, if you see, this is how the velocity profile comes up. Okay, the velocity at this section will be okay. So you have a velocity profile like this, so that the net flow at that section will be 0 in that case, okay. So if you at alpha is equal to -3, because obviously for the net flow to be 0, this guy has to be -3, okay. So alpha is equal to -3, so this implies h square by 2 mu u infinity times the pressure gradient value. This is equal to -3, okay. So of course you can cancel this minus actually. So now if you see, what are the different quantities? dp by dx is equal to 6 times mu u infinity by h square, okay. So you have this relation. So let us substitute the values. 6. What about the dynamic viscosity value? They might have given you. The dynamic viscosity is 4.7 into 10 to the power -4 SI units, okay. So 4.7 into 10 to the power -4 is what you have. U infinity. So what is free stream velocity here? The upper plate is fixed and the bottom plate is moving towards left at u infinity, correct? Actually you have taken the positive direction in the towards right direction, but here if you see, the plate is moving towards left, so that's why u is actually equal to minus, how much is the velocity? The bottom plate is moving at 0.3 meters per second, okay. So minus 0.3 meters per second, of course SI units. And now if you see h square, so what is the value of h square? H, the gap between the plates is how much? The plate spacing is 3 mm, okay. So if the plate spacing is 3 mm, so 9 into 10 to the power -6 basically here, okay. So 9 into 10 to the power -6. So if you simplify certain things, this can be written as 3, then this becomes 10 to the power -5. This gives you 10 to the power -1. So we have a 10 here, and this 3 cancels this 3 times, and this 3 cancels this 2 times totally here, okay. So 2 into 4.7, 9.4, 9.4 into 10, so 94, minus 94 pascals, okay. And of course width is 1 meter they have given you, so pascals per meter actually, so minus 94 pascals per meter, that's it, okay. So you have this value directly, minus 94 pascals per meter. So let us check, minus 94 Newton per meter square, okay. This is nothing but your Pascal, so pascals per meter actually, okay. So minus 94 Pascal meter, clear? A very simple question, okay. But of course you have to know what is the velocity profile, what is alpha, what is the dynamic viscosity value, clear? You have to be very sure with these kind of things. If you are clear with that, then we can write all these terms that are over here, minus 94 pascals per meter, okay. Clear? I hope it's fine, okay. So let's go for the next question quickly. So see, a metal ball capital A of density 3200 kg per meter cube is dropped in water, while another metal ball B of density 6000 kg per meter cube is dropped in a liquid of density 1600 kg per meter cube. If both the balls have same diameter and attain the same terminal velocity, the ratio of viscosity of water to that of viscosity of oil is dash. So obviously if a ball is actually moving in a fluid, then the terminal velocity is obtained by this relation. If the ball is in this direction, and let us suppose if the ball is moving with some velocity v, terminal velocity v in this direction, then definitely what are the forces that are acting on the ball. Obviously you have one weight of the ball that is acting downwards, So whenever the ball is moving vertically in the downward direction, the viscous effects will act in this direction, and also the buoyancy force acting on the ball. Of course, the balls are small, so buoyancy forces will be much small in magnitude, but let us consider for example. Okay, so this is weight, this is viscous force, which is nothing but your drag force, and this is actually your buoyancy force. Okay, so now whenever the ball is actually moving uniformly, then if you write the expression sigma Fy is equal to 0 for the ball to move in the direction, so sigma Fy, so if you see drag force, so what is the drag force? Half times CD. CD is nothing but 24 by Reynolds number for this flow, rho of the fluid into half CD, rho of the fluid into projected area. Ball is a sphere, so if you project it, you will get a circle. So pi d square by 4, pi d square by 4 into u square. So this, which is nothing but your v square here in this case. Okay, so this is actually your drag force. So drag force plus buoyancy force, density of the fluid g into pi d cube by 6. The diameter of the ball is pi d cube, so in that case you have pi d cube by 6. So this has to be equal to weight, density of the ball into g into pi d cube by 6 actually. So this is the total expression that you actually have in this case. Okay, now how you actually determine the viscosity? Basically from this drag coefficient, because in this Reynolds number you have viscous term. So Reynolds number is equal to density of the fluid v d by mu actually here. Okay, so rho f into v d by mu, so ball diameter is a d. So if you substitute that expression, you will end up with a mu sign. So if you slightly simplify this expression, let us see what comes out. 12 is actually here, and of course you have 3. Okay, so 3 times, so 3 divided by Reynolds number, so 3 times of mu divided by rho f v d. So this is this quantity into density of the fluid into pi d square v square plus rho is equal to, you can simplify this, is equal to density of the ball minus density of the fluid times g into pi d cube by 6. This is the term. Okay, so now if you simplify this, we have density of the fluid gets cancelled, v gets cancelled here, and d also gets cancelled. So this remaining one d can cancel this d square times. Okay, and what are the other terms you can cancel out? Yeah, I think those are the terms. Basically 3 pi into mu v is actually there here. Okay, so 3 mu pi v is actually have here. So 3 mu pi v is actually equal to, d got cancelled, right? So this is equal to density of the body minus density of the fluid times g into pi d square by 6. This is what you have. So this is the constitutive equation for the motion of the ball actually here. Okay, so now if you see, there are 2 cases that are given to you. So in the first case there is some fluid. So first case, if you see the first case, what you have actually here, in the first case, this fluid has certain different viscosity. So 3 mu 1 or a, they have talked about the fluid. Okay, let us suppose in the first case, if you see 3 mu 1 into pi times of velocity in the first case, this is equal to density of the body minus density of fluid 1 body in the first case into g into pi d squares by 6, pi d1 square by 6. This is in the first case. Okay, next in the second case, what happened again? 3 mu 2, in that case the viscosity is something different. Pi into v2 is equal to density of the body in the second case minus density of the fluid in the second case into g into pi d2 square by 6. Okay, so you have pi d2 square by 6. Now let us see what happens here. So if you divide these two, because they want the ratio of what they want, in the case A that it is dropped in water, and in case B it is dropped in liquid. So they are asking you ratio of viscosity of water to that of liquid. Okay, so let us see. If you divide these two equations, for example, okay, if you divide these two equations, then let us see what are the common terms you can cancel out. 3 pi gets cancelled, gg gets cancelled, this pi by 6 gets cancelled. Okay, now let us see one more thing. Ball A of density 3200, while another metal ball B of density 6000 is dropped in liquid. If both the balls have same diameter and attain same terminal velocity, so in both the cases the velocities are same and also the diameters are same actually. Okay, so these terms got cancelled. Okay, so these terms got cancelled. Then the ratio of viscosity of water to that of liquid is dash. So from this equation, if you see, mu 1 by mu 2 is actually equal to density of body minus density of fluid 1 in first case. So if you see density of body in the first case 3200, density of water 1000. Okay, so 3200 minus 1000, 3200 minus 1000 divided by, in second case the body is moving with a density of 6000, 6000 minus, what is the oil density here? Oil is of density 1600 kg per meter cube, so minus 1600. So let us simplify this result and let us get the value of mu1 by mu2. Okay, so this is equal to, obviously these two zeros and these two zeros gets cancelled, so 32 minus 10 22, 60 minus 16 44, correct? So this is obviously 2 times, so 0.5. So mu1 by mu2 is actually equal to 0.5 is the ratio of the dynamic viscosities of the fluids in first case to that of in second case. So they asked water to oil, so we got this expression directly here. Clear? So we have generated some constitutive equation for the motion of the sphere, and in both the cases we have divided so that we can cancel certain common terms, and finally we end up with the clear value. Okay, so mu1 by mu2 is actually 0.5 in this case. Okay, so this is what they are asking you, dynamic viscosity in the first case to that of dynamic viscosity in the second case. Okay, when they tell you just viscosity, you can just take dynamic viscosity values. Okay, unless and until they specify the kinematic word, you can just by default go for dynamic viscosity values. Clear? So did you all understand this question? It's a simple question and of course some nice conceptual question also. Okay, basically you have to understand this things, then you can just take this. Here we cannot neglect the buoyancy forces and all, because you see diameters got cancelled and also, but always whenever a fluid is moving, whenever a solid is completely immersed in fluid, definitely you should go for some buoyancy force involvement in the calculations. Clear? Fine. So clear, understandable. Good question, right? No need of calculator also. See, we have just calculated straight away. Okay, so let's go for the next question. Clear? So let's go for the next question. Let us see, something is asked. In order to predict the flow conditions after the turbine outlet, which is called tail ace of course, of a hydroelectric power plant, basically delivering 2400 meter cube per second. So this is the discharge in the actual power plant. A model of 1 by 75 scale is proposed. So basically, in order to do some experimentation, some 1 by 75 scale model of this power plant is suggested. Then the required flow rate of the model is dash meter cube per second. Okay, so let us see. If you want to calculate the discharge, discharge is equal to area into velocity. So if you take the dimensions, obviously the dimensions of the discharge is equal to L square into velocity. For example, let us say this. Okay, then in that case, discharge on the model by discharge of the prototype should be equal to length scale of the model by length scale of the prototype whole square into velocity of the model by velocity of the prototype. This is what you have. Okay, now let us see, length of model by length of prototype is known to you. It's given. We have developed a 1 by 75 scale model, but how you actually get the velocity relations? Now if you see, the flow out of a turbine will be actually the flow out of a hydroelectric plant. Actually, if you see, this is a free surface flow, because the tail ace is the part which is open to the atmosphere. So whenever you have some flow, then whenever the flow is actually getting out, then it's a free surface flow. Correct? Means basically on a surface there is some flow of the fluid. That's it. Okay, so in this case, since it's a free surface flow, your fluid number V by root GL is to be same, because it's a free surface flow, like in case of ships, all these things. Yes, of course, fluid number we have to use. So if you simplify this, this gives you Vm by, of course G is common term, so root of length scale of the model is equal to velocity of the prototype by square root of LP. So if you calculate this Vm by Vp, you need square root of Lm by Lp. So this is what you have the relation for the velocity profiles. The velocity of the model and the prototype. So if you replace here, this Qm by Qp is equal to Lm by Lp whole square into this Vm by Vp is nothing but square root of Lm by Lp. So if you multiply this root Lm by Lp here, you have totally Lm by Lp whole to the power 2.5 is what you have. Okay, so discharge in the model is equal to discharge in the prototype times length scale whole to the power 2.5. So this value is equal to, this implies QP is equal to QM is equal to QP. And what is the value of QP? QP is, in the prototype we have 2400 meter cube per second discharge. So 2400 meter cube per second discharge into this LM by LP, which is 1 by 75 actually here. So 1 by 75 power 2.5. So this many meter cube per second is the discharge that actually happens inside this model. Okay, so let us calculate this value. Let us take some calculator. So 1 by 75 whole power 2.5. Okay, so this value, this has to be multiplied with 2400. So 2400. So 0.0492. 0.0492 meter cube per second. Okay, so this is actually the discharge that actually flows to, yes, 0.049. Yeah, even I got the same answer. 0.049 is the correct answer then. So the total discharge to the model QM is basically equal to 0.0492 meter cube per second. Okay, so this is the discharge to the model that takes place. Okay, 0.0492. Okay, so clear. This is how we have the discharge to the model of this hydroelectric power plant. Clear? Okay, so please type in the chat box, is this clear to you? Basically it's a free surface flow, so definitely you have to go for the equality of the dimensionless number, which is fluid number. Okay, so let us see one more question. A circular cylinder 3 meters in diameter rotates at 600 rpm revolutions per minute. An airstream is moving at 100 meters per second, flows over the cylinder. Then the lift force per unit length of the cylinder is dash. So obviously there is a cylinder which is rotating. So you know, when there is a cylinder which is rotating, then if A flows over it, then there is some lift, which is of course the Magnus effect that happens. So that's why in our rotating bodies, what happens is basically whenever there is a flow, this cylinders generate some lift actually here. Okay, so now assume density of air to be 1 kg per meter cube and the force per unit length of the cylinder. Actually, if you see this rotating cylinders, if you see rotating cylinders, okay, so if you take this rotating cylinders, this is a combination of basically a uniform flow plus a doublet plus a vortex. The superposition of all these actually gives you the stream function or this velocity potential function, or the complex potential function for this rotating cylinder case. Okay, but right now the analysis is a bit complicated. Right now I'm not doing the analysis, I'm not doing the derivations and all, but I'll give you certain expressions. Okay, so see, basically the cylinder is rotating. The cylinder is actually rotating here. So whenever the cylinder is rotating, okay, so let us suppose if the cylinder is rotating in this case and there is some flow that is taking place over the cylinder. We have one more flow. So let us try to identify what is the flow or what is the lift on this cylinder. Okay, so now if you see this case, normally the speed of the rotation is how much? 600 rpm. Okay, so 600 revolutions per minute, 600 rpm. So obviously if you calculate omega is actually how much? 2 pi n by 60. 2 pi n by 60. Okay, so if this is 2 pi n by 60, then in that case we have 10. So total 20 pi radians per second is the angular velocity of the rotation of the cylinder. Okay, so if this is the rotation of the cylinder, then you know circulation is nothing but, you know, vorticity basically into means the rotation into the means basically the rotational velocity into the area actually here. Okay, so if you see, circulation is actually equal to v, the linear velocity, into the total area, which is 2 pi r into length. Of course length is given 1 meter, so 2 pi r into length, which is 1 meter. Okay, so what is the radius of the cylinder and what is v basically here? So circulation that gets developed in this is equal to, circulation is equal to v. What is v? V is equal to r into omega. Okay, and of course this is also 2 pi r actually, so 2 pi capital R. 2 pi capital R into 1 unit, because the flow is over the surface of the cylinder. So radius value is capital R. From this surface, if you take this, we have capital R here. Okay, so now if you calculate this value is nothing but 2 pi V is equal to R omega. So R square omega is what you actually have here. So this is the total circulation that occurs on this flow basically. So this is the circulation. Okay, so if this is the circulation, then definitely the lift generated. I'm not deriving these expressions because it's a just Abhyas course, so I'm just using the results. So the lift generated in this case of the cylinder is basically density of the fluid into the free stream velocity of the flow, which is basically in this uniform flow, if this is flowing with u infinity velocity, so rho u infinity into this circulation per unit length. Okay, so this is the total expression for the lift which is getting generated. So this is equal to rho u infinity into this basically this what do you say, this circulation is 2 pi r square omega, 2 pi r square into omega. So this is what you actually have. So here I think they have given you all the quantities. Omega is known, circle diameter is known, and of course this uniform velocity is also given. Density of air, they asked you to take 1 kg. That's it. Okay, so you have all the values. Let us substitute here. Okay, so if you substitute, this implies lift generated is equal to density 1, free stream velocity. So what is the free stream velocity? 100 meters per second. 100 into 2 pi r square. So what is the radius square here? So it's in 3 meters in diameter. So 1.5 is radius. So 1.5 whole square into this omega, which is 20 times of pi. So let us see what is the answer. This answer will be in newtons actually. What are the units they are asking you in? They are asking you in kilonewtons. Okay, so let us see. Of course per meter, because we have taken this length of the cylinder to be 1 unit. Okay, so cylinder's length is only 1 unit. So of course this is, we can write force per meter. So Newton per meter length. Okay, so let us calculate this value. Okay, if you want the answer in kilonewtons, you can delete these two zeros and 1 0 here, and you can write kilonewtons. Okay, so if you see, this is 2 pi or 2 into 2, 4 pi square 1.5 square. Okay, let us calculate this value. 4 pi square 1.5 square. Okay, so if you see 88.826, 88.826 kilonewtons per meter is the, yes, 88.62. Yes, we are getting 88.82, correct. Yeah, 88.82 kilonewtons per meter is the lift that is getting generated here on the case basically. Okay, so that's how we actually write the case. Okay, for vertex, for doublet, for uniform flow, we write these expressions in this way. Clear? Basically this is a superimposed flow. In case of this rotating cylinder, we have this uniform flow plus doublet plus vertex. These are the three combinations which generates you a flow or a rotating cylinder case, because in this case what happens, along with the cylinder, because of this vertex that is present, the particles actually rotate on this surface of the cylinder. Okay, and at every radius, obviously if you see, there is some rotation of the particles about that cylinder. So that's why this situation of flow can be designed as actually this situation of the flow can be designed as there is a rotating cylinder that is present physically, and there is some flow over that rotating cylinder. Clear? So that's how we can design this flow. Fine. So please type in the chat box, is this clear to you? Okay, since this is Abhyas course, we have restricted ourselves to, yes, kilonewtons. Yes, this is in kilonewtons. Okay, so I have studied FM from you, but in that I guess this lift concept is missed. Where you have studied basically in because this concept of lift and drag is very important for civil engineering students, so we have taught. But potential flows, normally if you see this, this concept is something different from that what you see in lift and drag in other cases. Okay, basically if you see in case of rotating cylinders and all, we deal in potential flows. Okay, and obviously for at that point I didn't take potential flows, I guess, if I'm not wrong. Okay, so whenever I teach potential flows, definitely I'll talk about this rotating cylinders and all the complex potential function, uniform flow, doublet and vertex, then we will see different cases. Like for example, in yesterday's case, we have seen half width or full width of a Rankine body. What happens at theta equal to 0, theta equal to pi by 2, theta equal to pi. We have talked all these locations. So similarly, when I talk about rotating cylinders case, next time in some courses, I'll definitely talk about all this, applications. I have taught now. Okay, fine. Then it's if it's in rotating cylinder, then definitely you might have had this in the last lecture at least. Okay, I think I still remember if I've taught for XC, then I was doing this in I've taught in the last lecture about the stagnation points, pressure difference, pressure coefficients, all these things. Okay, but right now since this course is for just a practice, I'm not dealing in derivations for that. Okay, but whenever there is some time, definitely I'll talk about, like in yesterday's class we have seen Rankine half body, width of Rankine half body, all these things. Okay, so similarly we'll go for things. Clear? Okay, so this is the last class, of course, and I think, yeah, thank you basically. So these are the things that we actually have here, and in this Abhyas series we have made some 10 lectures, some 10 good lectures, and definitely these problems will actually help you out to a very good extent in this GATE 2023, because if you see the kind of problems we have solved. Okay, so like the vertex flows we have dealt. Okay, we have dealt about the continuity equations, Bernoulli's equations, Venture meters, all the concepts. Okay, we have talked a lot about all the concepts in in actual case, and we have spent some 9 lectures on independent topics. Like for example, we started with the discussion on properties of fluids. We have seen certain compressibility, all these things. Then we have talked about pressure and its measurements. Then we started about hydrostatic forces and buoyancy and flotation as one single lecture. And then we started about 2 things, differential analysis and also integral analysis, basically control volume analysis of fluid systems. Okay, so that helped you out. And then after internal viscous flows, external viscous flows, we have dealt as 2 separate lectures. And of course, after that we came to turbulent and dimensional analysis, and the last lecture yesterday we have talked about potential flows, of course. Okay, but since we have certain time limitation now, it's basically the problem practice series. We are talking about these things, but crash course is being also started by Amit Dikshit sir. Yesterday it was started, and I think he's talking about laminar flows, so that crash course will definitely help you out to a very good extent. Okay, so please follow that crash course, then obviously solving these concepts and all will be much easier for you. Okay, because whoever teaches it, the subject remains the same always. So this is what I believe personally. So please follow that, and you can definitely feel much better and much more understanding in solving these questions. Okay, any more doubts or any more questions that you want to ask me? So please type in the chat box. Any more questions? So I think that's for my part for this Abhyas course for fluid mechanics. I hope you have enjoyed these questions. So almost every some 11 questions a day or 10 questions, we have solved some 100 plus nice questions, or most probable questions for GATE 2023. Okay. Yes, notes also available. How to purchase the course for GATE 2023? For GATE 2023, there is no course that we have launched. All we are doing for 2023 is for free. Okay, as of now. But of course, test series is about to come, and please make sure of this Gatopedia thing. Okay, we have uploaded the short notes actually here. Okay, we have uploaded the short notes pw pw.live. If you see, we have uploaded the short notes of all the subjects actually here. Okay, so I think it should be open. Okay, I think I got signed out. I'll sign in and show you how to take a copy of exit essays. All are there. Okay, I'll just show you. Just a minute. Let me start login here. So if you see this case, basically here we have a section called library. Okay, so if you go to the library section, then you see study material, Gatopedia. Okay, you have all the things basically. Okay, mechanical gate zone. If you see in gate zone, depending upon mechanical, civil, whatever, and of course for XC also we have here. So if you go for the mechanical zone, we have uploaded this Gatopedia, which is one very good. It's made by our own team actually. Okay. Fine. So we have talked about this. We have spent a lot of time actually on making this Gatopedia, and this is made by faculties. Okay, we ourselves have made this material, all the complete team. So that's how this is complete the short note. So if you can take a copy of this actually. Okay, so you can take a copy of this. So you can see a copy of this actually here. So I'll open it as a separate PDF. So if you see it as a PDF, we have this Gato PDF which is completely for free. So you see we have covered all some 13 subjects, and this is like a short notes kind of thing. This will definitely help you before you go for the examination. Clear? We have all the things, fluid and its properties, thermodynamics, whatnot. Okay, everything is actually present in this. Okay, Rajiv, how to purchase for the GATE course for 2024, sir? Yes, like this. So if you see here, if you go for this, and normally, oh, I think I'm sorry, I've disclosed it. Wait, Shift Control T. Okay, fine. So if you see, once you go here, let me show you. If you want to take anything, then just a minute, let me show you here. So here you have these things. Then if you go to batches, then you have seen you can see a lot of batches here. For example, if you type mechanical gate, in this case you have mechanical gate, all these things, and here you can go for the batches directly from this location. Okay, or if you go to PW store also, you can get a lot of batches and all, study material, courses, all these things, and basically you can get a lot of courses, study materials, all these things. And you see here also there is an option. If you click, depending on English or Hindi, you can click Prakaram batches or Shresht batches, then definitely they'll get displayed for you. Okay, so if you see, we'll get some batches like this. So depending on the of your interest, we can just click on that and you can go for the purchase. Just spend some time in using how just all over the app. Definitely it will be available for you. Okay, so complete notes of all subjects available. We are planning, but not very readily by today or tomorrow, but within very soon time. Maybe I can't tell you, but depending on the flexibility, will definitely work out. Okay, and whoever want to take something, you can just they can just roam over the app, our website. You can definitely find out the resources. Okay, so you told you have given shortly of Navier-Stokes equation concepts on last class. Okay, Navier-Stokes equations, basically if you see, let me take an empty slide at some location. Okay, we have some empty slide. So see here, Navier-Stokes equations. So if you see Navier-Stokes equation, normally during the differentiation or the derivation of Navier-Stokes equation, we talk in major about 3 types of forces. Okay, pressure forces, body forces, and also the viscous forces. Okay, so if you see the Navier-Stokes equation for incompressible flow, just a minute. Okay, so for incompressible flow, if you take this for incompressible flow, and of course assuming the fluid to be Newtonian fluid, all these things, then in that case your equation is something like the net force acting on the fluid means basically rho x bar minus del P plus mu times of del square V. This, if you see, this is equal to density times dV by dt actually here. Okay, so this is actually for the Navier-Stokes equation. Okay, and if you split the equation in 3 terms, then actually in x coordinate, y coordinate, and z coordinate, if you see, you can get rho xx minus dou p by dou x plus mu times of dou square u by dou x square plus dou square u by dou y square plus dou square u by dou z square is equal to density times of this acceleration, which is dou u by dou t plus u into dou u by dou x plus v into dou u by dou y plus w times of dou u by dou z. So this is how you actually write the equation in x direction basically. Okay, so here this is the Navier-Stokes equation in x direction. Similarly in y and z directions, you can write wherever there is u here. Basically in this expression, wherever there is u, you replace with v. Similarly, in this expression here, if you replace v and v, similarly here dou p by dou y, you will get the equation in y direction. So you should basically know, of course this equation don't have a solution till date, it's $1 million question. But now if you talk about some very simple flows, like for example flow between flat plates, okay, flow in a pipe, all these things, then here we need to make few terms as zeros depending on the approximations that we take. For example, if I am talking about a flow like this, let us suppose this plate is fixed and this plate is moving at some u infinity velocity. Okay, now if I write the differential equations, if I write the equations in y and z directions also, I have something like dou p by dou y plus mu times of dou square v by dou x square plus dou square v by dou y square plus dou square v by dou z square is equal to density times of dou v by dou t plus u times of dou v by dou x plus v times of dou v by dou y plus w times of dou v by dou z. Okay, we'll write this. Similarly, in the z direction also, if you write this equation, then what we have to do is, we depending upon the intentions, means if you take flow at any point, in this case the flow has velocity only in the x direction, it don't have velocity in the y direction, it don't have any velocity in the z perpendicular direction. So what we do, we'll say u not equal to 0, but both v and w are actually equal to 0, because you see general velocity profile at any point is given by ui plus vj plus wk. Okay, so this is the general velocity profile. So whenever you have the general velocity profile, now depending on the situation, what we write is, for example in this equation, so v is 0, so when you write v is equal to 0, all these terms turns out to be zeros. Okay, all these terms turns out to be zeros here. And body force, if you see, except gravity always acts in the vertically downward direction, but actually if you see, if you take this as x, y and z direction, if you see, we actually neglect this gravitational forces. Okay, we neglect this gravitational forces because here if you see, the flow happens because of the difference in pressure. Okay, so these are called pressure driven flows, and in case of pressure driven flows, you don't take the body forces into the effect. So depending on the situations, we assume certain terms out of these equations to be zeros, and actually we deduct some expressions for the velocity profiles actually here. Okay, but in main concern, if you take the Navier-Stokes equation produces a balance between body forces, this expression turns for body force terms, body forces, and this expression talks for the pressure forces, of course per unit volume, you can say pressure forces, and this term talks about the viscous forces, and this is acceleration of the fluid per unit volume actually here. Okay, so this is acceleration per unit volume. So generally what happens in all the pressure driven flows, basically means whenever the flow is because of pressure driven, what is basically this pressure driven flows and gravitational gravity driven flows? Let us see. For example, let us suppose if I take a plate like this. Okay, if I take a plate like this, then definitely what happens here is, whenever there is some flow in between this in the horizontal direction, then gravity has nothing to do with it. Okay, because gravity has its impact in the vertical direction, but if the flow is in horizontal direction, the flow is due to some other reason but not gravity. Okay, so generally in these kind of flows we call them as pressure driven flows. But let us suppose here, if I take an inclined plate like this, for example, let us suppose if I take a plate like this, if I take an inclined plate like this, and if I put some fluid, then the fluid flows because of the gravitation actually. Okay, instead of the pressure forces and all, rather than pressure forces, the fluid flows because of the gravitational force. Okay, so that's why when fluid is flowing because of the gravitational force, then these flows are called gravity driven flows. Okay, so when pressure driven flows are there, we neglect this effect of body forces, and these two will counterbalance each other. Viscous forces and pressure forces balance each other. Okay, this body forces term doesn't impact much. Similarly, when the flows are gravity driven, this pressure terms don't impact much, and we have this effect of body forces and viscous forces, because obviously at the end the fluid motion happens only when the viscous forces are overcome. Okay, so when viscous forces are overcome, then only we have flow. So which force dominates this viscous forces depends upon the type of the flow actually. Clear? Your Abhyas question says PDF available on PW, sir. Yes, it's available on PW app. If you open PW app and search, if you type Abhyas, then you can get this subject fluid mechanics, and you can get the PDFs after every lecture. Okay, so fine, I hope we had some enough discussion on this Abhyas series actually in this fluid mechanics. So definitely these 100 questions plus whatever the knowledge you have gained in solving this almost some 120 questions till date, if you see, definitely these questions will help you out in solving many other problems. Okay, because if you see, we have dealt concepts of almost all the topics that came in these questions, and which generally come in the subject when you talk about the subject. So that's why if you can solve all these questions, you will definitely have enough skills for solving all the GATE 2023 questions. Okay, so any more things, any more doubts? Fine, if there are no more doubts, we shall end the session. And this is the last lecture, so we have successfully finished this Abhyas on fluid mechanics. So from tomorrow, some other subject will definitely start for you. Okay, so type in the chat box, is this clear to all of you? Okay, fine then. Thank you all. We'll meet soon again on this channel with some other new content. Okay, thank you all. Till then, take time, keep preparing, don't stop your preparation, keep studying. Okay, and yes, try to attend all the sessions that means, of course, which are important for you. You really feel you can attend that always. Okay, so thank you all. We'll meet soon. Thank you.